get started. Welcome all to the second lecture of this semester of the Candidate Student Provost lecture series. I'm Jacques Verderschot from Physics, and I'm part of the committee who selects the speakers for this lecture series. It's always a hard task, although in this case it was actually pretty easy. Louis Ortiz, the advisor of Mohammad, will introduce Mohammad. Please go ahead.
Yes, so it's my pleasure to introduce my student, Mohammad Irfan. So Mohammad is a PhD in our department. He came to us from Bangladesh. In particular, he did his bachelor's and master's in the Bangladesh University of English and Technology. One of the interesting things about Mohammad, you should know, is his great diversity or variety of interest. He came to us with interest in computational geometry. In fact, he did some work there. He even did an internship at AT&T Labs Research, summer internship working on computational geometry. But he's also interested in machine learning and pattern recognition, and he did some work there. He did an internship in PricewaterhouseCoopers that involved some of that data analysis. But interestingly enough, he did some work with a very well-known person in pattern recognition, David Stark, on the authentication of Jackson Pollock's paintings, which is a very hard problem. And that essentially encompasses also an computer vision interest. When he came here, he worked because of his computational geometry interest. He worked with Professor Joe Mitchell from who has joined an appointment with computer science and applied math. Now, he also has teaching interest. In fact, he was a lecturer in Bangladesh, at the university where he got his degrees before coming here. And here he's also done some graduate and teaching internships. Now, obviously he has received several awards from both from Bangladesh and also from Stony Brook University, well, scholarships and fellowships related. I guess the final thing I want to say is it's related to his talk. Some of what you see was actually highlighted about 2 years ago, a year and a half ago, on this Science News. Some of you may be familiar. And this again, his work is on this interaction between the social networks and influence, and really takes a very interesting approach. And in the Science News, they make a very interesting connection that we actually completely missed about the fact that Arnold predicted that 6 senators were the most influential, and by that time, in fact, there was this final scan of 6 trying to put up the budget. It turned out that we're not the right 6, but it was 6, and it was an interesting connection. Well, so without further ado, my student, Mohammad.
Okay, thank you for the introduction. It's a great honor to present my PhD research here at the Provost Graduate Student Lecture Series. So today I'll be talking about influence in networks and how we can use game theory to find the most influential nodes, most influential individuals in a social network. This is a joint work with my advisor, Louis Ortiz. And usually people begin their talk with a quote from Einstein or maybe Galileo, but I'll begin this talk with a quote of Jay Leno. So you remember the fiscal cliff situation about a month and a half ago? So the automatic tax cut and the spending that was supposed to be enforced from January 1st this year, that would potentially lead the economy to another depression. So that was a very dangerous situation for the economy, and as Jay Leno says, it's 4 a.m. for our economy, and Lindsay Lohan is behind the wheel. So that situation was that much dangerous. And during all the negotiation that was happening during the fiscal cliff negotiation and all the coalition of bipartisan senators, we predicted using our model that that bipartisan group was influential enough to actually convince a majority of the senators to avoid this fiscal cliff situation. And that would happen with a chance of 97% or higher. And as you all know, that actually happened. And today I'll talk about how we actually gave that prediction using our model. So first of all, some overview about influence in networks. Today everybody has a smartphone. Maybe you are using an iPhone because some of your friends and family members, they are also using an iPhone. And nowadays everybody feels like they also need to have a tablet PC. Remember the time you were coming from New York City to Stony Brook using the LIRR train, and the guy opposite to you was viewing some videos on his iPad. And you thought, wow, this guy is really enjoying his time. Wish I also had an iPad. And maybe then you bought an iPad for yourself. And you can readily think that compared to that random guy on train, people in your social network, in your family, friends, those people might have a greater influence on you. And not only our social network, we also find that among the US senators in Congress, the way they, from their voting records, we can see that there's also, perceivably, there's also a social network among the senators in the Congress. And that is actually the topic of today's lecture. Okay, and most interestingly, a series of papers by medical sociologists Christakis and Fowler showed that this social influence is also evident in lots of other phenomena, like smoking or obesity, and even happiness. And so what do we want to do? First of all, we'd like to find most influential individuals in a social network. For example, who are the most influential senators in the Congress? And secondly, we'd like to study filibuster situation, especially who can prevent it. Those of you who are not familiar with filibusters, it's a procedure in the Senate where a senator can hold floor for as long as he wants to block or delay Senate action on a bill, unless 60 senators gather a vote against it. That is called cloture. So it has a long history all over the world, particularly in the US. We also, you can go back to 1933 when Senator Huey Long gave a filibuster 3 weeks long. And during that time, he recited Shakespeare. He also gave recipes for making soups. And most recently, Senate Minority Leader Mitch McConnell, interestingly, he filibustered his own proposal. So what happened is that he actually challenged the Democratic senators by saying that at that time the debt ceiling negotiation, the fiscal cliff negotiation was going on, and he challenged the Democratic senators by saying that give the whole power to the president. Presumably he thought that the Democratic senators were not actually that much united, so this will fall through. But the Senate Majority Leader Harry Reid caught that opportunity and called for a straight yes-no vote. And at that time, Senator Mitch McConnell did not have any other choice than to filibuster his own proposal. And so what do we want to study here? We'd like to know who can does there exist a small coalition of senators that can actually prevent filibusters. And similarly, number 3, we are also interested to study the influence of the gang of senators, the gang of 6 senators. It happened in this bipartisan coalition took place in 2011 during the debt ceiling negotiation, and we all know that it went down to the wire. So the question is, how influential were they? And other direction I'll show you here are Supreme Court rulings and also intervention to reduce smoking or obesity. So our first step in studying influence is modeling influence. We'll mathematically model influence in networks in a game theoretic fashion. And that game we call influence game. Here you can see a picture here consisting of several senators. It's a partial picture of 100 senators in Congress. And every game has 3 components. In game theory, every game has 3 components. Number 1, players. And in this case, the players are these senators. And you can see the rounded nodes they are represented. I drew the Democratic senators with blue color, Republican senators with red color. And the second component in a game is actions. So players will play actions. And in the Senate case, the senators vote yes or no. They have 2 actions. When a bill comes up, they adopt one of these 2 actions. And number 3 element of a game is the rule of the game. That can be, the formal term is sometimes best reply. So what is the rule of the game here? So we have these players in a game that are the senators. They vote yes or no. And I'm going to tell you the rule of the game here in the influence game model. So if you look carefully, some of the nodes are darker compared to the other nodes. For example, Senator Harry Reid, his node is very dark blue compared to Senator Schumer, it's light blue. And the darkness of the nodes here represents the threshold. And what does threshold signify? It signifies how stubborn a player is. For example, here, Senator Harry Reid is more hard to convince compared to Senator Schumer. And you can also see some connectivities, like these edges going from one senator to another, and some of the edges are thicker than the others. And in particular, you can see an edge going from Senator Schumer to Senator Reid. That has a number on it. You cannot see it possibly. It's 0.57. And this number represents influence factor. So how much a senator is influencing another senator. And you can see another edge going from Senator Schumer to Senator Jim DeMint. That is written in, that is drawn in red, and it has a number on it, minus 0.30. So these influence factors can be positive or negative. They signify the amount or how much a senator is influencing another senator. Presumably here, a Democratic senator is influencing a Republican senator by a negative number, whereas a Democratic senator is influencing another Democratic senator by a positive number. So there's a positive influence and also negative influence. And yeah, I'll get to it. So I'll first tell you the rule of the game here. The rule of the game is that when a senator, think about Senator Harry Reid. He has influences coming in from the other senators. And the rule of the game is that if the total influence on a senator exceeds his threshold level, that is shown in darkness level, if it exceeds his threshold level, he will vote yes. Otherwise, he will vote no. So that is the rule of the game. I'll give an example of the rule of the game, but first, the question Professor Warfschutt asked is, excuse me, how do we get these numbers? So that is the question he asked. So these numbers are learned using machine learning techniques from the senator's previous voting records. And it's a separate project in our lab done by John Honorio and my advisor. So let me give you an example of the rule of the game here. So we have an influence game. Think about Senator Jim DeMint here. He has influences coming in from his Republican colleagues as well as his Democratic colleagues. For example, Senator Paul, a Republican senator, is influencing him by +2. Senator Johnson is influencing him with a +5. Senator Schumer, -2. Senator Sanders, -3. So these are influences on Senator DeMint. These numbers are fictitious, but they are somewhat proportional to what we found in actual data. These senators have also made their choices. For example, here Senator Paul voted no, Johnson, yes, Senator Sanders, no, Senator Schumer, yes. Now the question is, according to the rule of the game, what should Senator D mean to do? What is his best reply with respect to all the other senators? And you can see I've drawn a barometer of influence here, and you can see a red line on 1. That level of 1 is Senator D means threshold, level of threshold. Rule of the game is that if the total influence exceeds the threshold, he will vote yes, otherwise he will vote no. So let us go through this example. First of all, the influence level, the initial influence level, is set to 0. Now you sum up the influences coming in from those senators who voted yes. You have Senator Schumer and Senator Ron Johnson. Sum these two numbers, -2 plus 5, you get +3. So at present, the total influence is at 3. Now you subtract the influences coming in from those senators who voted no. You get Senator Paul and Senator Sanders. They voted no. And sum up 2 minus 3, that is -1, and subtract -1, that is add +1, and you get to 4. So the total influence at this moment on Senator D mean is +4. And according to the rule of the game, his best reply would be to vote yes. And that is the effect of influence on Senator D mean. Now I described you our model of influence as a game where you have players, actions, and also a rule of the game that dictates what the player should do. And you can readily apply this same game to lots of other situations. For example, smoking. This guy is thinking what he should do, whether he should adopt smoking or quit smoking. And he has his other friends, some of whom are smokers, and some are not smokers. And he has different levels of influences coming from his friends, and he can adopt smoking or maybe quit smoking depending on what his friends or friends in social network do. The second step here is modeling practical situations. So I described you a model of influence as a game. Now how should we model practical scenarios? What are the examples of practical scenarios? One example is the fiscal cliff outcome, for example, which passed by 89 to 8 votes. Another example in Senate might be some other bill that passed by 60 to 40 votes. These are the practical scenarios that we see in real world. And in smoking, you can have a practical scenario, for example, 20% of some population are smoking. That's another practical scenario. So how do we model these kinds of practical scenarios using our game? So first of all, we view these practical scenarios as stable outcomes of a complex system. For example, this outcome of the fiscal cliff situation, that 89 to 8 vote outcome, is a stable outcome coming in from complex interaction among the senators. And we view this as a stable outcomes. And the way we mathematically characterize these stable outcomes is by what is known as Nash equilibrium. Nash equilibrium is the central solution concept in game theory that actually signifies stability. I'll go over in details what Nash equilibrium means and why does it encode stable outcomes. But first, something about Nash. Perhaps all of you have heard about John Nash, who won the Nobel Prize for his seminal contribution in Nash equilibrium. And many others also know him from the movie A Beautiful Mind. But most interestingly, the movie, actually the way they defined Nash equilibrium in the movie was completely wrong. It was a bar scene where John Nash went with 3 other friends to the bar, and they met, there was these 5 other ladies that came in the bar, and they were deciding whom to propose. So in that situation, the director, Ron Howard, mixed some of his creative imagination in the definition of Nash equilibrium, and by that he got the definition completely upside down wrong. So I'm going to give you the correct definition of Nash equilibrium here. Whenever somebody asks you in the street, tell me what is a Nash equilibrium, you can give this definition in one line. That is, In a Nash equilibrium is a situation where everybody best replies to everybody else. So it's that simple. It's a simple concept that says that nobody has any incentive to adopt a different behavior. Everybody is already playing his best with respect to what the other people are playing. That is Nash equilibrium. And it signifies a stability because nobody has any incentive to move. That is why it's stable. So let me give you a flavor of Nash equilibrium in our setting. So we have this model of influence where we previously found out that Senator Demin's best reply would be to vote yes with respect to the other senators. Question is it a Nash equilibrium? Well, we cannot answer it as yet because we only found that Senator Demin's best reply is yes, but we also have to verify that every other senator here, you can see, is also playing his best reply. For example, is Senator Schumer playing his best reply, which is yes? You can think of Senator, if you consider Senator Schumer, he has his other friends from which he is getting influence, some Republicans and some Democratic senators, and these senators are also voting yes or no. So the question is Senator Schumer best responding? And you ask the same question with respect to every senator. And if everyone is best replying with everybody else, with respect to everybody else, then that situation is a Nash equilibrium. And it is, in our case, we model stable outcomes of a system using this concept of Nash equilibrium. For example, this fiscal cliff outcome, that is, we can think of that as a Nash equilibrium. Okay, so as a reminder, we model practical, we think about practical scenarios as a stable outcomes, and we model stable outcomes using the concept of Nash equilibrium. So, so what is the root of influence games? The model of influence games, it has roots in mathematical sociology, especially Schilling's residential segregation. Those of you who have a background in sociology already heard about it. Schilling gave his model in 1971 based on threshold level of tolerance. So what does it mean? A person will change his residence from one area to another area if the proportion of opposite race exceeds his threshold level of tolerance. And you can see the New York area residential segregation here. I'll zoom in on one part of it. You can see various colors. Green, the blue colors represent African Americans, red, whites, green, Asians, and yellow, Hispanics. And you can see that in the Jamaica area, you have a residential segregation with majority of African Americans. In Bayside, you have a majority of whites. And in between these two, there's a small strip which has a rich mix of all races, all four races here. So, and later on, Mark Granovetter extended Schilling's model to a very widely applicable area. And he published his seminal work, Threshold Models of Collective Behavior in 1978. And interestingly, at that time, when he wrote the paper, he was a professor here at Stony Brook in sociology department. And after he published his seminal work, he moved to Stanford University. So as a reminder, our model of influence game, we have this model of influence where in a game theoretic setting, where we have these senators as players in the game, and they have these actions of voting yes or no, and they also have an influence, they apply influences on each other, and we also know about the rule of the game, what should be the action of these senators based on their influence level and their threshold level of tolerance. And we model practical scenarios using the concept of Nash equilibrium. That's just giving you a reminder. Okay, so let us go to the most influential individuals and our formulation of the most influential individuals. The input to this problem are an influence game where you are given players, actions, and rules of games. and a desirable outcome. So what is a desirable outcome? A desirable outcome might be avoiding the fiscal cliff situation, or passing the healthcare bill, or going through the debt ceiling bill, or in other scenarios, a stable outcome might be reducing smoking by 10%, or maybe reducing obesity by 15%. Those are desirable outcomes. And with respect to the desirable outcomes, a set of nodes, a set of individuals will be called most influential if they can influence everyone to strictly follow this desirable outcome. For example, in the Senate case, if you want every senator to vote yes on some bill, and perhaps that is your desirable outcome, with respect to that outcome, a set of senators will be called most influential if they are able to convince everybody else in the Senate to strictly vote yes. They will not have any other choice, other senators, other than voting yes. In that case, that group of senators will be called most influential. Let me go to some examples. For the 110th Congress, which ran from 2007 to 2009, the question is, who are the most influential senators? So I've drawn the influence game here. The blue nodes are Democratic senators, red nodes are the Republican senators. You cannot see the names here, but you get the idea that the Democratic senators are kind of clustered together. The Republican senators are also kind of clustered together because of their influence structure. So first of all, we found this network, these connectivities, and the numbers that were these influence factors using machine learning techniques. Secondly, we computed stable outcomes of the system, that is computing Nash equilibrium of this game. And thirdly, we find the most influential nodes of this system with respect to some desirable outcome. For example, if you want everybody to vote yes, then select a small group of senators such that if they vote yes, then everybody else will also vote yes. They will be that much influential. And I should note here that all of these three problems here are actually computational problems, and I'll not go into details of the algorithms or the techniques we apply in solving these three problems, but I'll give you a snapshot of the results that we got. For the 110th Congress, we have 6 senators as most influential, and it is a bipartisan group of 6 senators, 3 Republican and 3 Democratic senators. We have Senator Kerry, Enzai, Inouye, Bennett, Sessions, and Lautenberg. The implication is that if these 6 senators vote yes in Congress, then everybody else will also vote yes. And secondly, there is no ranking here. You cannot say that Senator Kerry is more influential than Senator Enzai. No, that's not the case. It's a collective thing. Collectively, these 6 senators are most influential. So for the 112th, the recent Congress, which ran from 2011 to January of 2013, you can ask the same question. Who are the most influential senators? Here, I've also drawn the network here, network of influence here. It looks kind of the same. The blue nodes are kind of clustered together. Red are also clustered together. And for this Senate, we found 10 senators to be most influential. And again, this is another bipartisan group consisting of 5 Democratic senators, including Senator Sanders, and 5 Republican senators. We have Senator Reid, Senator Enzai, who was also in the previous most influential nodes, Senator Sanders, Crapo, Inouye, Johnson, Reid, DeMint, Hagan, and Collins. So together, these 10 senators consist of the most influential senators in the last Senate. So one question might arise about this number. So in the 110th Congress, we had 6 senators as most influential, and now we have 10 senators as most influential. So what can be an explanation for that? So you know about the people nowadays talk a lot about polarization in Senate, polarization, and it's hard to convince everybody to come together into consensus. I think our result actually signifies that, that anecdotal evidence. That is, previously, only 6 senators could actually influence everybody else to come into a consensus. But nowadays, it's very hard to get everyone to come together. And that number 10 actually signifies that. I'll give you another anecdotal evidence in a bit. So let's go to filibuster situation. The question is, does there exist a small coalition of senators that can prevent filibusters? For the 110th Congress, yes, if you have Senator Kerry, Senator Roberts, and Senator Graham, together they can prevent filibusters. How? If they vote yes, then it will guarantee that at least 60 senators will vote yes on a bill. So that will prevent filibusters. And similarly, you can ask the reverse question. Does there exist a group of senators that can actually lead to filibuster by voting no? And in the 110th Congress, we have Senator Kerry, Nelson, and Senator McConnell. Together, if they vote no, then 60 senators will vote no. Thereby, I'm sorry, you cannot get 60 senators to vote yes if they vote no. So they are influential in that sense also. So number 3, so gang of 6 senators. This is a bipartisan group of senators, 3 Republican and 3 Democratic senators here, that was formed during the 2011 debt ceiling negotiation. And we all know that that actually went down to the wire. So the question is, how influential were they? Using our model, we found that in 90% of the cases, they are not influential enough to actually make a majority of 60 senators to come into consensus. So they are not actually that much what we've written here, quote unquote, not powerful enough. Although this statement is based on purely a mathematical model, it also has an anecdotal validation. The validation comes from the gang of 8 senators that was recently formed in 2012. So here we have all of the gang of 6 senators here. On top of in addition to that, we have 2 new senators here in this gang. And we have Senator Bennett and Senator Johans. And this gang, from gang of 6 to gang of 8, they had a similar responsibility to avoid the fiscal cliff situation. And during the fiscal cliff situation, we also saw a consensus between Senate Majority Leader, Senator Harry Reid, and Senate Minority Leader, Senator Mitch McConnell. And so we have a group of senators that was trying to influence the other senators to reach a consensus. And using our model, we found that in 97% of the outcomes, the majority of the senators will be influenced by this bipartisan group. And as you know, in the early hours of the new year this year, Senate actually passed a proposal that could not make either group happy. It was kind of in the middle. The Democratic senators were not happy with the proposal. The Republicans were not happy with the proposal, but they were influenced by the bipartisan group to actually come into a consensus, and that bill passed by 89 to 8 votes. And that is actually consistent with our prediction here. But I should also give a small note here. That is, when the voting took place, one of the gang of 8 senators, Senator Bennett, he actually voted no. He later told New York Times journalist Maureen Dowd that he was not actually satisfied with the spending cut deal in that proposal. Even with that wrong assumption, small wrong assumption, I think our prediction was correct. So we can apply the same situation in Supreme Court, same model in Supreme Court. The US Supreme Court has 9 justices. Some of the justices are known to be more liberal than the others, and Justice Kennedy is kind of in the middle. So you can ask the same question in this setting. who are most influential set of justices. And here, a most influential set of justices consists of two justices, one from the liberal side and the other from either Justice Scalia and Justice Thomas. So these two justices together will be most influential in convincing everybody else. And now I'll breeze through some snapshots of technical results for people who came from computer science or game theory. I'll just very quickly go through this. So our contribution to game theory, we showed that the influence game model that I presented earlier is actually equivalent to two-action polymetrics games. That has been studied for a long time, beginning in 1968. So all the technical results we have will also apply to that classical setting. So when we have non-negative influences in an influence game, that game has a very interesting property that is known as strategic complementarity. And when we have symmetric influences, for example, Senator J and Senator I, they are influencing each other with the same number. In that case, that influence game will be a potential game. That is another interesting, very interesting class of games. And potential game is the brainchild of Monderer and Shapley. And you know that Lloyd Shapley, he won the Nobel Prize last year for his contribution. And another interesting class of influence game is not symmetric, is non-symmetric, yet it is a potential game. And we do not know about any large class of games in game theory that has this property, that is a non-symmetric, yet it is a potential game. So the contribution to computational game theory in terms of complexity, we know about several classes of complexities, computational complexity classes like NP-complete, co-NP-complete, and sharp-P-complete. These are provably extremely hard classes of problems to solve. And we showed that existence of a Nash equilibrium in pure strategies, even in very simple types of graphs like bipartite network, is NP-complete. And many other variants are also NP-complete. So these are all very hard problems. And uniqueness of a Nash equilibrium that is co-NP-complete, counting the number of Nash equilibrium that will be sharp-P-complete, and given all the Nash equilibria, if you are asked to find the most influential nodes problem, it is computationally inapproximable beyond a log factor. So that is also a hard problem. So we basically characterize the hardness of all the computational problems that we faced in this research. But we gave fast polynomial time algorithms for tree structured influence game. So influence game where the network has a tree structure. And for general cases, we gave effective computational schemes. And we also gave a provable approximation with log factor for finding the most influential nodes. So that's, I'll finish the technical snapshot here. Now, what does the roadmap ahead look like? There are several problems that we can think about here. First of all, the computational problems. Learning the question Professor Barf should ask, how do you get these numbers? We can actually improve the learning schemes by leveraging studies from political science. Those of you who come from political science background know about the constituency influence in US House of Representatives, a paper by Stokes and Miller. Similar studies can actually, we can leverage similar studies in our setting to learn this influence structure and the influence factors, those numbers. And a second problem that we can go for in the future is computing Nash equilibria or computing stable outcomes in very large scale scenarios. For example, the social network for smoking or obesity that has thousands of nodes. And a related application of our model would be minimal targeted intervention. So what does it mean? I'm going to give you an example. So at the beginning of the talk, I talked about Christakis and Fowler, medical sociologists. They showed that there's an evidence of social influence in smoking, obesity, and even happiness. And this is the picture for the obesity case. They started the the data from Framingham Heart Study, and they plotted individuals as nodes here, and the size of the node actually is proportional to the body mass index. And the yellow nodes are medically obese, that is their body mass index is above 30. Now you can also see another thing, that is the yellow nodes that are the obese individuals, they are kind of clustered together. And the question we might ask here, how can we actually intervene this network, this social influence here within limited budget? For example, it would have been great to actually convince everybody in the network who is obese to eat healthy, but we all know that that's not possible. Maybe we can convince 20 people or maybe 50 people, and we can give them maybe weight loss programs, free weight loss programs, or we can give them, we can convince them to eat healthy. So within a limited budget, how can we select a small subset of these individuals? If they were to eat healthy, then they would actually influence many other people around them to eat healthy, and that would maybe reduce the level of obesity by 10%, for example. So, and that question is exactly what we frame as most influential individuals question. And using the Framingham Heart Study data, we can actually give answers to those kinds of questions. And you can ask similar questions for smoking. How can we select, for example, 100 people? If we were to convince them to quit smoking, then it will have a significant effect on the whole network. Maybe it will reduce smoking by 20%. So you can ask all those interesting questions using the model I described. And with that, I should conclude. I started writing a blog recently relating my research to US political scenarios. You can read the blog from mtirfan at .blogspot.com. I must thank Professor Charles Tabor, Laurie Caron, and many others in the grad school for arranging this talk. I thank Professor Barbshute for hosting this talk. I'm also grateful to my advisor, Luis Ortiz, my lab mates, Hao Chan, and other lab mates for giving me so many suggestions for this presentation. I'm also thankful to my wife and my son. I gave a dry run last night in front of them, and my wife gave me many useful tips, but my son, unfortunately, he could not understand anything. But he can be excused because he is only 2 years old. So with that, and last of all, and most importantly, I thank everyone here for coming to my talk. Thank you.